Welcome back. This is Walker Physics, Chapter 6, and we're in Section 6.5 today on circular motion. If you were to move anything in a circle, it's going to require a force to do it. And the easiest picture in my mind is going to be if you were to have a tether ball or some kind of a ball like a volleyball on a rope, and then you are around and around and around like David's sling. As you pull it around, you're forcing that object to not go straight the way it wants to, but to actually move in a circle, continuously in a circle. So if you were to ever break that string at any point or let go of the string, that ball at that moment will go in a straight line, because Newton's first law said that objects in motion tend to stay in motion in a straight line. At a constant speed unless acted upon by an external force. So if there's nothing acting on it at all, then a moving object would move in a straight line forever. Well, that object, say this red pink ball that you have here, wants to go in a straight line at whatever its forward velocity is. So in the case on the left side, the velocity is heading northeast. But as it tops the round of that curve, it's now going southeast. Well, you have changed the velocity, and you remember a change in velocity over a period of time is called an acceleration. So even though that this velocity might be constant, you might be going around at the same speed all the time, just because it's changing directions means, since it's a vector, it has a directional component to it. If I'm changing directions, I have changed the velocity. If I've changed the velocity, I've accelerated. That means there's an acceleration just to going around a circle, even if you're going the same speed. That's the reason why when you are driving a car, you slow down into a curve, and then as you go past the middle point of that curve, now you can speed back up. Because otherwise, the speed of the curve, there's an acceleration that will result in your car going off the road, even if you haven't increased in speed. Okay, there are highway markers that say this turn is a 40-degree turn, or this is a 50-degree turn, whatever. So the direction of the force that's causing the acceleration, remember, if you're changing the velocity, you're changing the acceleration. If the force that's causing that to go in a circle or causing that acceleration is always towards the middle of the circle. So for instance, if you have a tether ball, the force that's making that tether ball not go straight but curve is the tension in the string. The force that's making the Earth go in an orbit that's a curved orbit and not a straight line is the gravity of the sun. The sun is pulling that planet continuously, and that force is changing the velocity, and as it changes the velocity by changing its direction, there is an acceleration. Okay, so that's called a centripetal force, and that's called a centripetal acceleration. So I'm going to try to show you what I'm talking about. Let me find my pencil. All right, ignore this. I will not test on this, but I learned it, so I want to at least teach it to you. So if you've got a circle, like we're talking, let me move this down. If you have a circle, say, that has a certain radius, okay, so this is a radius, and you've got a velocity going in this direction, okay. In a certain amount of time, this dot will continue around the circle and be going in this direction. Okay, so that means my velocity here, in whatever direction it is, okay, minus the other way, because they're going in different directions, that's the change in velocity over the time it took to move around that circle, okay, is called the acceleration. That's the change in velocity over time, right? So here's what we got. V minus a minus v is 2v over t. Okay, that's your acceleration. All right, now, if this velocity is not changing, if it's a constant velocity, then we just have our third grade rate times time equals distance. Okay, let's solve for t and substitute. So I've got t equals distance over velocity, and I'm going to put it in for t, and I have 2v over, okay, x. Now do you see, divide by fraction, you reciprocate and multiply, which means that is 2v over x. But what is x? X is the distance from here to here, which is 2r. So this is going to be equal to 2v squared over 2r. So your acceleration is going to be equal to v squared over r. Okay? Now, so that's something that you will use over and over and over again. So this is one of your formula. The acceleration is going to, your acceleration is going to be v squared over r. Okay? Now, put v squared over r in for a. Do you see we have force equals mass times acceleration? If you put this in for a, then you're going to get centripetal force equals, you're going to have centripetal force equals your mass times the square of your velocity over your radius. Okay? These are your two formula that you're going to be using continuously through this section. Okay? So at least write it in your notebook, if not in your brain. So, what is the force? I think a sling or that tether ball is the force in the string, because I think that makes sense. If you break the string, the ball would fly off in a straight line. Okay, so that kind of makes sense. That what's keeping that ball going around and around and around is you tugging towards the center continuously. Okay, so that tension is the force that's causing that centripetal force towards the center. There's a force towards the center. So, for instance, I've got a ball. It's going in this direction, okay? But I have a force going down, so it's going to move slightly down, okay? But now it's going in this direction, and I have a force that's going down, so it's going to be moving slightly down. Okay, now I have a force, I have a direction, and the direction of the force is always towards the center, and so you end up with a curve. So all of your forces are always acting towards their center. So this is centripetal force, force sub Cp, centripetal force, and the acceleration that centripetal force causes is called the centripetal acceleration. That's A sub Cp, okay? And it also goes towards the center. So it may be a little harder for you to guess what is your force on a car that's going around a curve. What's causing you to go around the curve? Well, it has to be a force. Well, you have an engine in your car, but that's making you straight. What is the force that's causing you to turn? And if you think it all the way to the end, the only force that's causing you to go around the curve is the friction on the tires. The frictional force of the rubber on the road is making you go around the curve. Otherwise, imagine a road covered in ice. You go around the curve, you instantly slide off to the right. If you're going to the left, you slide off to the left. If you're going to the right, you're going to slide off towards the outer rim of the circle. Okay, so the friction is your force, and it's the centripetal force moving towards the center.
So the same applies whether you're going on a banked curve or you're going around a dip. Any type of a roundness is going to have circular motion. So at the top, you've got a banked curve, like a NASCAR track. And actually, that helps you to stay around the curve because not all of your friction has to go in one side. You've got a portion of your weight that's actually moving towards the center, which helps you a little bit. In the case of going around a dip, I don't know if you have ever ridden in the car when you were small and you go down a dip and everyone screams, and you go around a hump and everyone loves it. It's the same idea. You just got a different circle. Rather than a left-right radius, you've got an up-down radius, and you're going to, all of this will contribute to your circular motion. It's exactly what you do when you want to make a roller coaster for someone to ride. You want them to go around curves sideways. You want them to go around dips and bumps, curves and circles. All of that is fun because you're playing with gravity when you do that. Also, I don't know if I'm going to do any of these problems because they sound awful to me, but an object may be changing its speed as it moves in a circle. So if there is a change in speed, like when you slow down going into a curve when you're driving, you are changing your forward velocity. So there is a tangential, meaning like this a sub t going around the circle. You've got an acceleration, centripetal acceleration going towards the middle of the circle, but you also have a tangential acceleration going forward because you might be speeding up or slowing down as you're going around a circle, which only makes everybody's lives worse. So if we're going to do math about that, please never ever speed up or slow down. Actually, you should slow down or you'll probably die. So please slow down, and we may still not do any math about it.